Our next presentation will be from Richard Koppenberger, who will be talking to us about automation for accommodating fuel-efficient descents in constrained airspace. He's leading NASA's development of the Efficient Descent Advisor, which supports concepts such as tailored arrivals and 3D path arrival management for optimized profile descents under a variety of traffic conditions. He began his career with NASA in 1988 and has been a lead researcher on numerous projects in the areas of microburst wind shear detection, rotorcraft obstacle avoidance, and air traffic management. His BS is in aerospace engineering from the University of Arizona, and his MS is in aeronautical and astronautical engineering from Stanford University.
Good afternoon, everybody. So what I'm going to try to do is kind of give you an overview of the technology that we're developing for the air traffic controller to better accommodate fuel-efficient descents under constrained or busy traffic conditions. And as you'll see, this is really where the potential benefits are greatest, but unfortunately it's also where the problem is hardest to solve. But luckily we're getting lots of help with this problem. We're working very closely with our partners at the FAA. We're also working very closely with industry, especially Boeing. So to illustrate the problem, what you're looking at here are vertical flight tracks of Boeing 777 operations into San Francisco over a 2-week period. And they're color-coded for various times of day. And the blue and the purple tracks represent airplanes arriving during busy or congested times of day. And so what you see here is the classic dive and drive type approaches where controllers level these aircraft off. And in some cases, these level-offs occur for as much as 60 nautical miles. And of course, any time an airplane has to be leveled off, it requires additional power on the airplane to maintain level flight. And along with that comes excess fuel burn, emissions, and noise. And it really comes down to the fact that this is a very difficult problem for the human being to solve on their own, to try to come up with a fuel-efficient profile that acknowledges all of the various spatial and temporal constraints in the airspace. So the way controllers deal with this is that they tend to issue very tactical type commands. They'll step the aircraft down in altitude. And if I can move on to the next slide, looking at the lateral flight profiles, they also issue very tactical type heading commands, and what you don't see here are speed commands that are issued throughout the process. Again, controllers are constantly iterating on acknowledging or adhering to these various constraints in the system. So this is really a problem that is calling out for automation, and it's really unfortunate because all the airplanes that you see in these tracks are equipped with the latest avionics capability. From the airplane's point of view, it's more than capable of planning and controlling to a very fuel-efficient profile. But again, once it enters this busy arrival airspace, the pilots seldomly get the opportunity to leverage that avionics equipment. So the approach that we're developing is to develop a tool, a controller decision support tool that we refer to as the Efficient Descent Advisor, or EDA for short. And this capability is based on generating trajectory predictions, not just for the arrival aircraft in the system, but really for all of the aircraft throughout the airspace, including overflights and departures. And in that way, we can strategically develop solutions that not only allow a continuous, fuel-efficient descent, preferably at idle thrust, all the way from cruise altitude to landing, but we can also strategically accommodate the various other constraints in the system. First and foremost, we need to worry about conflict avoidance. Obviously, there's no point in developing a nice strategic type solution if there's a high likelihood that the controller is going to have to interrupt that trajectory in order to respond to a downstream conflict. We also need to worry about arrival constraints or throughput constraints. We want to maximize the throughput within the capacity constraints of the system. What we don't want to do is get into a situation where we start to sacrifice throughput in trying to meet our efficiency objectives. Traffic demand is only expected to increase as we move towards the future. So EDA is designed to work synergistically with existing scheduling automation that's already deployed, namely the Traffic Management Advisor that NASA was involved with and has now been deployed at all of the air route traffic control centers in the United States. So the kinds of solutions that we develop with EDA are simple speed and path type clearances, even though we're basing our solutions on complex 4D trajectory computations. Ultimately, what we want to send up to the flight deck are simple parameters such as speed and path type clearances. And the idea there is so that we can issue these clearances by voice in a near-term environment, and in a further term environment, we can issue these clearances by data link. Data link provides an additional capability. With that capability, we can provide a richer set of solutions that can accommodate even more complex constraints. But we are trying to target a near-term voice environment with our initial implementation. And last but not least, we want to make sure that our automation is compatible with the existing flight deck automation on the aircraft. We want the pilots to be able to use their flight management systems and be able to guide and control the airplane according to the EDA advisories or clearances that are sent up to the flight deck. So we're pursuing EDA development really as a two-pronged effort. First and foremost, we're relying upon human-in-the-loop simulation. We're using feedback from our controller teams in order to refine the algorithms within the prototype itself, as well as developing the procedures and the phraseology that are necessary to communicate these trajectory-based clearances, which span areas of airspace on the order of 20 minutes in terms of look-ahead time horizon. But we're also employing flight testing. That's another vehicle at our disposal for perfecting this automation. And we're using flight testing primarily to validate the underlying trajectory predictions. This automation is really only as good as the trajectory predictions upon which our solutions are based. So we've spent a lot of time looking at how accurately we can predict idle thrust or continuous type trajectories and make them available for this concept. And what you're seeing here in this photo is the FAA's Global 5000 aircraft. We were out at Denver last year flying with this airplane, as well as involving United and Continental Airlines in flying over 300 flights where we issued EDA type clearances, and we were able to look at the accuracy and precision of our trajectory predictions based on that data. And in fact, we'll be back out at Denver in just a few weeks conducting a similar type flight test, but with a different level of aircraft equipage, focused initially on the higher performing larger jet aircraft where they can fly idle thrust type performance-based type descents, but we're also interested in lower levels of equipment where they fly more geometric flight path angle type descents. So looking at some of the results from our simulation studies, what I'm showing in this first plot is a case where, is a baseline case where we did not have our EDA automation running. All the controllers had at their disposal was the scheduling tool, namely the traffic management advisor. So they were left to their own devices to come up with maneuvering solutions designed to target those TMA arrival times. And again, you see the classic stair-step type pattern where airplanes are leveled off, leading to inefficient type flight profiles. Once we introduced our EDA automation, however, we were able to see that most airplanes could execute a continuous descent all the way from cruise altitude down to our control point, which in this case was a meter fix at 10,000 feet, providing the fuel benefits that we were seeking and, of course, the emissions benefits that go along with that. So I talked about flight testing. One of the flight testing activities that we got involved with, working closely with Boeing, was tailored arrivals. Tailored arrivals is a concept where by data link, we can deliver all of the clearance information to the aircraft that specifies the entire arrival trajectory all the way from cruise altitude flight, in this case out in the oceanic airspace, all the way to landing. And the idea is to specify the terminal area portion of that trajectory as a relatively static type profile where we supply the airplane with any speed and altitude restrictions that need to be acknowledged in the terminal environment. And so that gets included in the data link message, but we also incorporated EDA type clearances, where EDA was applying control in the upper airspace with simple, in this case, simple speed cruise speed and descent speed type clearances in order to target the delivery of that airplane to the meter fix, which in this case was the Point Bryony with a crossing restriction of 11,000 feet and 240 knots. And again, all of that information was sent up to the airplane by data link. And this is really a proof of concept type activity. We have not left EDA out in the field. The automation is not being used yet by the controllers. We're still working on that with our human loop simulations and tech transfer efforts. But the procedures that we had developed, working with Boeing on tailored arrivals for accommodating these trajectory-based solutions have been already fielded. In fact, Boeing is flying tailored arrivals up to this date with United and Continental, Air New Zealand, as well as Qantas Airlines. And so looking at some of the potential benefits that can be afforded with a concept like tailored arrivals, what we looked at post-flight was 3 different baseline conditions representing light, medium, and heavy traffic congestion. And what we see here is that the bulk of the benefits lie in the constrained or heavy congested airspace environment. And for a large aircraft, 777 aircraft in this case, flying into a highly constrained airport like San Francisco, we were able to estimate fuel savings on the order of 3,000 pounds per flight, with a corresponding reduction of 10,000 pounds in carbon dioxide. And we also computed savings of the other emissions that we, of course, are concerned with, the various nitrogen compounds and the unburned hydrocarbons, et cetera. So we were also interested in looking at the potential noise benefit. Obviously, the noise benefits come as the aircraft traverses the lower altitudes. And so with the help of Boeing, what we did was estimate the noise contours based on the baseline set of flights. This is what happens today without any automation. And you can see that the noise is relatively dispersed throughout the peninsula. These are all flights, of course, arriving into San Francisco. And we noticed a particular pocket of noise right over the community of Woodside, which has been a source of many complaints to the San Francisco airport. But once we introduced the tailored arrival concept, at least modeled those trajectories, we were able to show that the noise was dramatically reduced in terms of its overall dispersion, and that it was concentrated mainly in the final approach corridor. In this case, the noise being focused over the bay, over the water, where the impact to the surrounding community is minimal. So in summary, we've determined that the bulk of the benefits of flying these continuous descent type approaches really come in doing so during very congested or constrained airspace conditions. And NASA is working very closely with our government and industry partners to develop automation that can address that problem. And what we're doing is trying to transfer this technology to the FAA in a relatively near-term time frame, bridging that proverbial valley of death, as we heard about yesterday. And in fact, we plan to complete our initial phase of tech transfer next year. And so the FAA is really behind this all the way, targeting a potential deployment date in the 2016 to 2018 timeframe for a voice-based application of this technology. Thank you.